So what we're going to do now is we're going to start talking about Java 8 and some of the basic Java 8 features. You've seen these things throughout the semester. Now I'm going to kind of go through them a bit more systematically so that you'll have a better idea of how they all work. First, we'll start by talking about the key aspects of functional programming, which is at the heart of a lot of the Java 8 features that are built in the language. And I'll talk about how functional programming is applied in Java 8, and then we'll look at a bunch of examples. So what is functional programming? Functional programming is essentially a declarative paradigm. So what that means is the program says what logic you want to have performed without describing the control flow or the explicit algorithmic steps of how to perform that logic. So another way to look at it is that functional programming focuses on what computations to perform, not on how to compute them. That's the responsibility of the implementation of all this stuff to do that. Here's a very simple example, which actually is not unlike some of the stuff you're doing for the next assignment. I'll talk about that in a second. So this is an example. I just called the function zap. And zap is going to take a list of strings or lines, and it's going to filter out ones that match this omit parameter. And then it's going to return a new list with those strings omitted. So this is the declarative way to do things. You say lines, which is a list. Convert yourself into a stream. So there's a factory method called stream that you can use to convert a collection into a stream. And that'll create a stream of all the elements in this list. And then you're going to filter each line in this stream. And if the line doesn't equal what you're trying to omit, then you let it through. Right? So we're going to filter the stuff that matches this expression, which has to be negated because we're trying to get rid of stuff. So we're going to let through everything that doesn't equal the thing we're trying to omit, which sounds a little weird, but we're basically filtering out the stuff that doesn't match. So anything that matches the omit, we're going to negate that, and then we'll let stuff through that doesn't match. And then we're going to collect the results of this filtering process, turn them into a list, and return that filtered list as the result of the zap function. That's how you kind of read that. A couple things that always throw people for a loop, and we'll talk more about this later. You know, like where the heck does this thing come from and what's its type, right? So we'll talk more about that. In a nutshell, the line here is shorthand for, you know, string space line. So it's a line. It's defining a variable called line of type string. And of course, that comes from the stream of strings that came out of this list. And we'll talk a bit more about the syntax. It's a little bit weird when you first see it, but once you see it a couple times, you get used to it. Yes, Hamid?
What is the benefit of using strings? It's not just a syntactic sugar.
Yeah, the question is, what is the benefit of doing this? We'll talk in depth about that, but in a nutshell, it allows you to focus on what you want to have done, not how it's done, and most importantly, it scales up really nicely to running in parallel on multi-core processors. So that's the real win for our purposes here. There's lots of other benefits too. Yes?
Would this be the same as saying like for line in lines, and then you would say omit articles?
I'll show you the normal code here in just a second when I show you the imperative way of doing things. So we'll come back to this. By the way, this is very similar to what you need to do for your submit all method for assignment 4A, except instead of filtering, you'd put a map. You'd put a map operation. You would map things. So for assignment 4A, what you do is you have a list of, or you have a collection, and you want to turn that into a stream. You have a collection of callables. And so you're going to take that collection of callables, you're going to turn it into a stream, and then you're going to map each callable that comes from that stream, and you're going to submit that to the executor service that was passed in as a parameter. And remember, submit returns a future. And so the output of map is a stream of futures, and then you're going to collect all those futures into a list and return that as the result of submit all. So that's essentially how that works. It's really, really concise. Yes?
If you turn a string to a string, and this new string will not be stored in the new space, in memory.
So let me see if I understand your question. So in this particular case, in this program, we're converting a list of strings into a stream of strings, and those will then be, converted into a stream, which is sort of think of it as like a temporary buffer, like kind of like in the Unix pipeline model, you can pipe things together. It's a temporary buffer that stores that stuff on its way to being transformed by one of these so-called aggregate operations like filter or map. So yes, it will create a temporary data structure and it'll store it in there as it's flowing through the stream. Other questions? Okay. So in contrast, the classic object-oriented programming we know and love, have been using for a long time, is so-called imperative. And that basically says you are telling the computer what to do. So you're saying, do this, do that, in this sequence. So imperative program focuses on describing how a program operates via statements that change its state. So going back to Jesse's question, here's the same logic in a classic imperative style that we just looked at in the declarative style, right? So there's the declarative mode. Notice we just said, here's what I want to have done. We didn't say how it worked. Over here, we're going to say, create an array list for every string in the list lines parameter. If we don't have a match, then add that line to this result, to the list of strings that's ever growing. And when we're all done with this loop, return the result. So that's the imperative way of doing things. And you'll notice, I mean, again, for something this simple, they look almost equivalent. It gets a lot more interesting when we start looking at more complicated things. And one of the things you'll learn as we go through this is you can compose new aggregate operations, new processing modules in a stream in a way that is almost trivial to do, but it has great effect and great power on what you're doing. All right, so that's the imperative way of doing things. Under the hood, functional programming is based on something called lambda calculus. You may or may not have taken that here at Vanderbilt. Basically, it's all about treating computations as the evaluation of mathematical functions and typically stringing these things together. So here's an example. You have some input, which is usually a stream of input, but there's an input. And then you have these transformational functions. And this function works on its input, and it outputs the result of the function. And then that output is passed to this next function, which takes the result of this function as input and creates output. And that's passed along to another function, which takes the input. So it's basically like a bucket brigade that processes things as they move through these functions that transform them. And in so-called pure functional programming, you can't have side effects. You can only transform things as they flow as input and output from functions. Java is not a pure functional language, but you can treat it that way if you so choose. And it's a good idea to do that because if you do it that way, you can end up avoiding the need to do any other kind of synchronization. And the reason for that is you're not actually changing any state. State is never changed. And the data is never changed. It's simply transformed as it flows through the stream. And if you go back and read the literature about synchronization mechanisms, you'll see their purpose in life largely, though not exclusively, is there to ensure that state is modified in some kind of sequential order. And if you don't end up modifying state, the impact on how you program is quite profound, and the ability to scale and parallelize things is wildly improved. Now, it's not always as easy to do it as it is to say it, but that's the idea. Try to eliminate side effects. Yes?
What do you mean by state?
State, so a value, right? So anytime you have a value anywhere that needs to be protected from concurrent access, that's an example of state. So a good example that we've looked at over and over and over again in this, what's an example that we've done in every single programming assignment in one way or another that involves state?
The available volunteers.
Right. So we have some kind of map of the Palantiri, the magical seeing stones, and we've got n of them typically. We've got Palantiri count number of them, and that Palantiri manager state, in other words, whether the Palantiri were available or not, that's the state, that was being accessed by multiple threads, right? The beings that were gazing at it. And all that stuff that you guys had to do with synchronized blocks, with reentrant locks, with all the other stuff that we've done over the course of the semester, has all been about trying to protect that state from unfettered concurrent access. Because if you had unfettered concurrent access, what would happen if we had unfettered concurrent access? What's the bad thing that would happen? Starts with an R. Race conditions, right. So the state would be perturbed. It would be modified in incorrect ways. So that's what state is. State are things that need to be protected from unfettered change. Yeah, Ann.
Can you explain why it's a problem for like the functional solution with the for each loop, and why it's not a problem for the stream?
Well, if you do it right, so the question is, why is state a problem? Now, keep in mind, by the way, this is a very simple example. So this example doesn't illustrate that point. We'll see other examples later that do. The key thing to note is if you do this right, the elements that flow through this stream should not be dependent on each other. They should be separate, thereby lending themselves to embarrassingly parallel processing, because they're able to not have to have any dependencies or shared state. And so as a result, we'll see a little bit later, probably next week, when you have something that has this property that nothing depends on anything else, you can transparently replace stream here with parallel stream. And a parallel stream will then do some magic to take whatever the stream is that you're working on and break it up into pieces, invisibly to you, by something called a splitterator. And then that splitterator ends up creating little chunks of data, and those little chunks of data get handed off to a pool of threads using a fork-join thread pool. And that fork-join thread pool then runs each of those things concurrently, does them all in parallel, or many of them in parallel, and then joins all the results back later. So it allows very easy, very scalable, transparent parallelization without having to modify your program much at all. And so you can often, not always, but you can often go from this sequential processing model to a parallel processing model just literally by changing stream to parallel stream. And that's a huge win, as you'll see when we get into some more examples. Okay, so in contrast, object-oriented programming is not about transforming functions in a pure way at all. It's about what I like to call hierarchical data abstraction. So you'll typically think about modeling your data and the operations that access and manipulate that data in a hierarchy, right? So you have like some kind of base interface or base class, and then you subclass various other things. And the way it works is that the components, which are really the units of programming, are based on these stable class roles and relationships, and they can be extended via inheritance and dynamic binding. So functional programming is about functions, hence the name, computation, chunks of computation. Object-oriented programming is more about classes and data encapsulation. So at some level, they couldn't be further apart, right? Because they're completely dealing with different things. So object-oriented programming does not decompose the system based on actions. It decomposes it based on data structures and stable data relationships. And the way that you handle state in an object-oriented world is you hide it by methods that perform imperative statements. So here's a simple example of this. We have an iterator, and we're going to iterate through a data structure in some way, like a list or whatever. And these methods, like has, next, and next, hide the actual representation of how the data is structured. So we can write this program, and we don't care how it's structured. Is it a linked list? Is it a binary tree? Is it an array? We don't care. We're just going to program based on these abstract interfaces, these abstract data structures or data types, and all that stuff is hidden from us as a user of this. All right, so now we'll talk in a second. It turns out that those two paradigms can actually coexist quite nicely, like peanut butter and chocolate in a Reese's peanut butter cup, right? And they're actually even tastier, right? Peanut butter is pretty good by itself. Chocolate's pretty good by itself. But man, when you put the two together, it's really fattening. No, it's really tasty, right? Because I eat too much of it. But you'll see in a second that the combination is actually more powerful. So Java started adding functional programming features around March of 2014. So that's about 3 years ago or so. And they added some things like lambda expressions and method references, which we'll talk about here in a second. And then they also added this thing called Java Util Stream, which is this really, really, really cool package that allows you to be able to do functional operations on streams of data. And we'll talk more about that. So in a sense, Java 8 is a hybrid language that combines functional and object-oriented paradigms by allowing you to have the intersection of the two things. And this is the way, by the way, every programming language that wants to remain relevant in the modern world is moving. Everybody's adding functional programming features left, right, and center for the reasons we'll talk about here. What the functional features do to Java is they help close the gap that historically has existed between the domain intent, in other words, what problem you're trying to solve, and the computations performed to carry out that domain intent. Historically, there's been a gap. You had specifications and you had implementation. And objects got you part of the way there, got you a little closer to domain intent, but you still have an awful lot of work to do, and it was difficult to deal with certain things like concurrent access. So the domain intent defines the what you're trying to do. So here's a simple example that we'll talk more about if we have time, which is an image processing app where you can give it a bunch of images and it'll do various image processing operations on it. And here's how you could program this with streams and functional programming. So you can see here, this is really quite easy once you know what it means. We say, I've got a list of URLs. I want to run this list in parallel, all the things that are about to happen. I want to run in multiple threads of control simultaneously. I want to get rid of any images that are already cached. So in other words, if they're already on my machine, I'm not going to download them and process them again. They're already there. So I filter my list of URLs, get rid of the ones that already have stuff locally. What's left over, I'm then going to download each image, and then I'm going to apply a list of filters to each image. And when I'm all done, I'm going to collect the results into a list of downloaded and filtered images. Right? So that's how you say this thing declaratively. And now when you first see it, you're like, what the heck is going on here? But once you learn how to read this stuff, it's really easy because you're just saying, turn this list of URLs into a stream, get rid of the ones that are already cached, download and filter, and collect the results into a list of images. So the cool part about this is telling you what you want to do, not how to do it. And you can actually see this. This example is on my website, which you can play around with. It's really, 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 really cool. So what it's essentially doing is it's making it more, it's helping to connect the domain intent, which is what I want to do, with how I do it. And if you compare and contrast this very, very concise way of doing things with the more traditional approach, which I also have on my website, you'll see very quickly that it's a big win in terms of comprehensibility. And it also scales up trivially to parallel processing. This is not to say that object-oriented approaches are now irrelevant. They're still relevant. In fact, they're very relevant. And they're relevant because object-oriented features are crucially important to help to structure the architecture of your solutions. So if you were to peek inside the implementation of what I just showed you, you would see that I have really cool object-oriented abstractions to be able to say there's a concept called an image stream, and then I have all kinds of different ways of implementing this thing. And I use inheritance to demonstrate that. And I have this concept of a filter, and I can use object-oriented techniques to have different kinds of filters and so on. And so object-oriented programming and classes provide the basis for the architecture of the solution, which is really, really important, arguably as important as the computations. But the functional programming can work very well when you decide what computations you want to do to make them easy to express. So anyway, we don't have a lot of time to go into this at the moment, but as we talk through some examples, you may get to see this. So I'm a big fan of combining the architectural benefits of object-oriented approaches with the ease of computation of the functional programming approaches. And Java 8 brings them together. So it's a very powerful hybrid approach. Now, if you want to use Java 8, you're going to have to get a Java 8 JDK and JRE, Java Runtime Environment. So you'll have to go out and get them. And they keep updating them. They're very mature and stable at this point. You can get that from Oracle. If you want to use Java 8 with Android, you'll need to get more modern versions of Android. So they've backported some of this stuff to earlier versions, but the really good place to start is with API level 24 and beyond. So I think they're on 25 and 26 now. so you have to go and download that. That's Android N, Nougat. And late-breaking news, I recommend getting Android Studio 2.4 or later. You can find out how to get that if you go to this link, because this has really good support at long last for Java 8. Earlier versions of Android Studio and Android had kind of sucky support for Java 8, so it took a long time to compile your programs. But with the latest versions, they've added some new features, and it's really fast, and it's just as fast as using the earlier versions of Java and earlier versions of Android, because they have the instant run incremental compilation stuff. And if you want to see examples of this stuff, you can go here, and if you take a look at the Java 8 folder at this URL, you'll see lots of examples, and I'll walk through a bunch of them here shortly so you can get a chance to see what they look like. All right, so that's an overview of the basic Java 8 features. Now that I've given you a quick overview of functional programming and just a kind of a teaser about all the great stuff in Java 8, let's talk about the real concrete features. So we're going to talk here first about lambda expressions, and then we'll talk about method and constructor references. So let's talk about these things. So you've seen lambda expressions. I've used them throughout the course, but we haven't really talked about them in any deep way. So a lambda expression is basically just an unnamed block of code which may or may not have parameters. And you can store a lambda expression in a field or in a variable and pass it around and execute it later. So here's a very simple example, probably the simplest example. This is where we're going to create a new thread, and we're going to give a lambda expression that says print hello world when the thread runs. So this is the lambda expression. This is just saying this lambda expression takes no parameters. And here is the piece of code that is going to be run when the thread is started. This is what the code would have looked like if we'd done it in more traditional Java 7 and before versions, right? So we would have had to have made ourselves an anonymous inner class instance, which would have said new runnable, open close paren, open curly brace, public void run, open close paren, curly brace. You know, here's the code, bloppity bloppity blop. So what lambda expressions are doing is it's getting rid of all that syntactic sugar. So it's probably, you could argue that lambda expressions were added by people who suffered from repetitive stress injuries, and they were tired of typing all these semicolons and extra stuff and curly braces and so on. So they just got rid of all that stuff and came up with a syntactic way of being very concise. So I think you'll agree with me that this is way more concise than that. Now, if that was the only win, it would be of limited value, but there's a lot more things we're going to be able to do. That's a lambda expression. We'll talk more about those shortly. There's also something called a method reference, which is basically a name for something, for a method typically. And you can use this to get even more concise syntactic relief from repetitive stress injury. And we'll see here that there's a bunch of different kinds of method references. There's a reference to a static method that looks like this, a reference to an instance method on a particular object, which looks like that, a reference to an instance method of an arbitrary object of a particular type that looks like this, and then most interestingly perhaps a reference to a constructor, which is called a constructor reference. We'll talk about this example here, and we'll come back and fill in the other ones later. So let's take a look at this, and we'll see how each of these approaches makes the result more and more and more easy to understand by getting rid of extra syntactic stuff. So let's say that we have an array of strings of people's names, and we want to sort the contents of that. So here's one way to do it. This is the classic way of doing it in Java 7 and earlier, where we make a new instance of an anonymous inner class, new comparator string, public int compare, string s, string t, blah, 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 blah. Okay, so that's kind of the classic way of doing things. You can see it's a bit verbose, and you look at that code and you're not quite sure what it's doing at first, right? You can't just stare at it and know what it's doing. You have to read it. Here is how to do this with a lambda expression. And this allows us to omit all this ugly syntax. So this says sort name array s and t, which is what's called type inference. I'll talk more about that in a second. And then it's going to go ahead and take s and then compare it to t. So this is the way of doing this with lambda expressions. Here's the way of doing this with a method reference. All these do exactly the same thing. They have exactly the same overhead. It's just that this is way, way more easy to understand, right? So this says sort name array and make the comparison compare to ignore case. So I don't know about you, but I would much rather look at that kind of code than this kind of code, which is better than that kind of code, right? So that's the improvement you get. That's what a method reference is doing for you. So it's generally a good idea to use method references whenever you can. And the cool part is that IntelliJ and Android Studio will tell you when you can do these changes, and they'll also do the changes for you. So you'll get a little thing in your compiler window that says, you know, would you like to change this to a lambda expression or a method reference? And if you say yes, it'll do it for you automatically. Yes, Duncan.
Is sort here just an arbitrary name? It can be anything.
Yeah, it could be anything.
The comparator market is what actually does the sort.
So this is, I mean, there's a method in the arrays class called sort, which is intended to sort arrays, hence the name. So there's nothing special about it being sort. It's just that sort expects to have a comparator to decide how to arrange the sorted values. And so this is simply replacing the verbose version of the comparator with a method reference version. But you could do it for other things. And we'll see some other examples in a second. So let's take a look at another example. So here's one way to print the contents of a collection. So one way to do this is to have an array, and then we're going to say we're going to print out the results by saying arrays as list name array, and that's what it prints out as the result. Here's another way of being able to do this using streams. This is kind of fun. And so what this does is we can say name array, convert that into a stream. So we're going to stream.of. Stream is a class, of is a method. So this is saying create a stream of the contents of name array. And then for every element, which is a string in this case, for each element, print. So that's another way to do it, right? And we'll look at some other examples in more detail in a second to help make this all more clear. So the third example I want to look at, or the third part of this lesson, is going to look in more detail at other kinds of Java 8 features, in particular something called functional interfaces. Yes, Gabriel?
When you want to use string, so like in the previous example, would you be okay to just use name array dot for each?
You'd have to say, OK, so the question is, let's see. The question on the table is, in the previous example we'd looked at, we said name array, which was an array. You have to, name array was a built-in array. And so you can't for each on a built-in array. So you have to convert it to something you can for each on. And so the way to do that, there's several different ways to do that, but one way to do it is to turn it into a stream. And that stream.of takes a built-in array and turns it into a stream of the elements of the array. So we're going to talk about functional interfaces now. And they plus the lambda expressions and method references provide kind of the foundation for all the concurrency stuff we're going to talk about later. The concurrency stuff, in my mind, is really the most interesting part, but you have to understand at least a bit of the basic syntax to make any sense of the stuff that's coming now, or coming next. So let's talk about functional interfaces. A functional interface contains only one abstract method. By the way, does anybody who's a movie buff know what the obscure reference is to this car? What kind of car is that? It's a Highlander. And why can there only be one? No, this is terrible. There used to be a movie, great movie called Highlander. There can be only one. It's like, has to do with zombie killing vampires or something like that. It was cool. I think Sean Connery was in it. OK, way too obscure. So a functional interface can only have one abstract method. Runnable is a classic example of a functional interface. It has one method. And a functional interface is used as a parameter where a lambda expression or method reference is passed as an argument. Now, again, this may not make a whole lot of sense until you see the examples, but we'll look at them in a shortly. Java 8 defines many, many, many different types of functional interfaces. There's like 24 different types. We're just going to focus on 5 of the most common of them: predicates, functions, consumers, suppliers, and by functions. So let's take a look at a predicate first. You've actually seen these before, but I'll define them and I'll show you some examples. A predicate is a functional interface that performs a test that returns either true or false. So if you take a look in the Java function package, you'll see there's an interface called predicate, and it has a single method called test that takes some value t, which is parameterized, and returns true or false. Here's a simple example. We're going to make a list of integers, and we do that by saying new array list, arrays as list 1, 2, 3, 4, 5, right? So that we're making a list, and that is going to be used to initialize this list, which is a list of integers. And then we're going to go ahead and print the list out so you see what it is. And then we're going to go ahead and we're going to use a predicate lambda. So what this is saying is it's saying remove anything in this list that is even. And this is a lambda expression that says I, where I is the element in the list, you know, from 0 to size minus 1. For every element I in the list, remove it if I mod 2 equals 0. So in other words, if it's evenly divided by 2, right? It's an even number. So what's so funky about this is this looks like a function call. This looks like you're going to pass a parameter, which is the result of this, to remove if. But that's not what it's doing at all. It's passing in a lambda expression, which is a predicate lambda expression. And this predicate will be evaluated every time the remove if method needs to figure out whether something should be removed or not. And here's the really funky part that takes a long time to get your head around. You'll notice that there is no method called test here. This is an expression that matches this signature, right? So we're going to pass in a predicate which is going to take a t and return true or false. And so this doesn't have to say test anywhere. This is basically what is going to be replaced as the implementation of test. So if you went and looked at the remove if implementation, you would see it takes a predicate lambda and it calls test on each element in the list. But this is the replacement for that predicate lambda. That takes a long time to get your head around, so you'll just have to take it on faith for the moment, but it's really cool. This particular syntax is actually shorthand. So I is shorthand for integer I. And this leverages what's called Java's type inference capabilities. So the Java compiler can properly infer that I must be an integer because list is a list of integers. So it's able to figure this out for you. Now you could say integer I here if you wanted to, but nobody would do that. It's way too much carpal tunnel syndrome, right? So you just let it infer that stuff. All right, so that's one example. This is a pretty cool example. The other thing to note that if this was some kind of concurrent data structure, like a concurrent list, remove if would be done atomically. So it would be doing that computation with the lock held. This one is just a simple list, so it doesn't matter, but it could be done atomically. Let's take another example. This is the function interface. We saw that when we looked at the timed memoizer in the memoizer class. So a function is an interface that takes that has one method called apply, and apply has one parameter, which is the value that's passed in, like is this a prime number, and it returns a result, like what's the factor for that prime number, what's the smallest factor. So that's what the functional interface looks like. Here's a simple example. We're going to make a list of threads where we're going to have 3 threads in the list, and each thread is given a name, Larry, Curly, Moe. Who are those guys? All right, good. Nobody knew my Highlander reference, but everybody knows the Stooges. That's I don't know if that's good or bad, but it's good. All right, so we have 3 names. And now what we're going to do here is we're going to print out the original list. Then we're going to sort the list, and then we'll print out the sorted list. So sort requires a comparator, right? We already talked about that. You have to have a comparator for this stuff. So we're going to sort the list. And what we're going to do here is we're going to pass in a method reference, which is essentially a function. And the method reference is going to take a name and it's going to get the name back, and then we're going to have that used by the comparing function. So we'll see what comparing does in a second. Here is comparing. So this is comparing, basically is going to, comparing is implemented like this. Comparing is going to take 2 values, the 2 values we're comparing at a time when we're sorting something, and it's going to go ahead and apply the key, and so it's going to go ahead and apply this to the value that was in there, like the string, and it's going to compare that to the other one. So it's going to be doing basically comparing with the name that comes back. So this is how we can basically compare these values using a function. So you can see here this is the functional interface that's being used to get the value and then compare it to another value. So that's the function. The example that we did before for the memoizer is probably a little bit easier to understand in some ways. So this thing is passed a function, and it does the comparison. There's also another interface called a bifunction, and a bifunction takes two parameters in its apply method and returns a result. So as you can guess, bi means two, right? We have two parameters that are passed to the function. Yes, Ethan?
Are they predefined, or do we define it ourselves?
Good question. So these of course are predefined. These are part of the Java util function package that comes out of the box with Java, but you are welcome to define your own functional interfaces. And I'll talk a bit more about what that means in just a second. So here's a really fun example that illustrates a bifunction. So here we make ourselves a hash map. This is no longer a list. This is a hash map of strings to integers. And we're going to put the IQ levels of our intrepid stooges in here. And then I'm going to show you two different ways of changing the IQ levels, right? So here's one, and this is the one that uses a bifunction. So you can see it takes two parameters. We're going to replace every key value pair by replacing the value by subtracting 50 IQ points from every value that's in the map. So this is going to go through the map, and for every key value pair, it's going to update the value field by subtracting 50 from the current value. And that's a bifunction right there. It's got two parameters. Here's how we would write this if we didn't have Java 8 bifunctions and lambda expressions and so on. So you can see what we'd do here is we'd iterate through the map, through its entry set, and we would set the value of every entry by subtracting 50 from the value of the current entry. Now, aside from the fact that this code is way more concise than this code, can anybody else see a win of doing it with this as opposed to doing it with that? So one thing is we don't have to write all this extra syntactic sugar and do all this stuff. But what's the other thing that's going to be more effective with this than that? What if this wasn't a hash map, but it was concurrent hash map? I'm sorry? Right. Replace all is atomic. So we can give it a function to apply on every element, and replace all will make sure that that application is done in an atomic way. Whereas this code, I don't even know how we would do it without a lot of extra work. We would have to figure out some way to lock it, and it would be ugly and a real pain in the butt. So this code is way better for a lot of different reasons, one of which is it's very concise. OK, let's also talk about some more functional interfaces. So the ones I'm talking about here, by the way, are just the most common ones. There are lots more, but these are the ones that we've used a lot, and you'll use a lot if you program with Java 8. So here we have something called a consumer, which accepts a parameter and returns no results. So it consumes the data. And here's an example of a consumer. So in this case, we're going to have an array of our favorite stooges. And then we're going to go ahead and, for each of the elements, we're going to go ahead and print them out. And so it turns out that print line is a consumer that accepts a string or whatever, usually a string, that we're going to print. And so we're going to go ahead and for each of the elements here, we're going to go ahead and print out the results. And print line is basically a consumer function because it takes of data in and it has a side effect, namely printing it somewhere, but it doesn't have an output, it doesn't return a value in particular. And it's interesting, by the way, does anybody know the secret by which a thread is turned into a string to be printed with println or printline? There's a method that there's a method defined as part of class object that every Java object has. What's that method called? ToString, right. So it just calls ToString. OK, so that's an example of that. And then the final thing is a supplier. So a supplier returns a value and takes no parameters. So it's kind of the It's kind of the reverse of a consumer. Consumer accepts the result and doesn't have a return value, although it may have a side effect, as we saw with print line. Supplier is just the other way around. It returns a value and takes no input. And we'll see there's a couple of different ways to show this. I'll show you several different ways of doing it. So here we have a person map that maps string to string, and we're going to put various characteristics of each type of being. So we have demon that's naughty, an angel that's nice, and so on and so forth. And then we're going to look up in the map and see whether or not, what the type of the person is, right? So we're going to have a person, and so we're going to say person map.get. Now, if we put in demon or we put in angel, then what we're going to get back here is going to be a string that is naughty or nice, right? But what if we put something that's not in there yet, like demigod or something like that? We have no idea what that's going to do. In fact, it may return us null because it's not in the map. Well, we're going to do something really cool here. We're going to use another Java 8 feature called optional. And optional is a little wrapper you put around something, and it will allow you to be able to deal with nulls as if they were actual objects, because by default, null is not an object, so that means if you try to access anything on it, it'll blow up. But optional lets you do that. So what we're going to do is we're going to say, take the result that comes back from get, and if it is null, then put it into an optional, and then optional has some magic methods you can use on it to avoid crashing. This is what's called the null object pattern, by the way. And so what we're going to do then is we're going to say disposition of person is going to either be disposition, in other words, it's going to be like naughty or nice or whatever, or we're going to go ahead and just give it the results of this lambda expression. So or else get will simply say if this thing is null, then return unknown. And this is a supplier because it just gives a result back. In this case, it's just giving back the string unknown. So that's, again, yet another example of suppliers. Here's perhaps some, and look up more about optional if you want to learn more about how that works. Here's another example of a supplier interface. This actually has its own name. It's called a constructor reference. So here's an example where we have a little class, and it's got a main program. And what it does is it makes a supplier, and that supplier is given the constructor reference for the class itself. So supplier now has a constructor reference. And then we can come over here, and we can say supplier.get. And supplier.get will call the constructor for its parameter, which in this case is this class. And that will return a new instance of the class. And then we're going to go ahead and print the result of calling hello. So this is going to return a new CRDemo object, and then its hello method will get called. The key point here is that we were able to assign a supplier to a constructor reference, so when you call get, it'll go ahead and make a new instance of that object. Yeah? Is that like the same as like an object factory? It's an object factory, exactly, yes. Now here's some other really cool things. So Java 8 now has this concept of default methods and a functional interface, in addition to having an abstract method, can also have default or static methods. And that's kind of weird at first, and we'll talk about it. So here's an interface that Java defines, comparator. You can find comparator in Java. And you can see that comparator has an abstract method called compare. So that's what makes it a functional interface. It also has a bunch of default and static methods. Like there's a default method called reversed. Here's an interface with a default method that actually has an implementation. This is new to Java 8. Previously, you couldn't have method implementations in statics. You couldn't have method implementations in interfaces. Now you can have default method implementations. We also have a static method defined here, which have implementations. Now here's another thing. There's also a method in comparator called equals. And this is actually inherited from Java lang object. So there's a bunch of abstract methods in Java lang object, and those don't actually count as being part of the abstract method count of an interface. So anytime you override something from Java lang object, that doesn't count as an abstract method. So we still only have one abstract method, compare. There's also equals, but that's going to be, it overrides the one that's there, but it doesn't count against our abstract method count. All right, so that's the end of part 3 of this discussion.